All right, Physical Organic Chemistry, Ch7.2.4, a brief video lecture covering section 7.2.4 and 7.2.5. That's chapter 7 out of our textbook. We're going to discuss transition state theory and how it applies to selectivity. Okay, now we're considering a kinetically controlled reaction. Okay. Now again, our purposes in this are how do we make this useful for a synthetic chemist? Well, there's an assumption that goes into using the ratio of the products to backtrack to the activation barrier between them. And in fact, we've looked at this. In fact, I've given you a handout in class for the thermodynamically controlled reactions. And we can make an assumption here. An assumption that works, but is not actually accurate. Okay? And that assumption is that the two transition states for two products are in equilibrium. Okay. Now this isn't actually a factual or valid assumption, but the mathematics of it all works out, and we're going to look at a connection from our textbook. So with this, you can take that ratio that we have seen before, that we've calculated in the delta G0 calculations, and apply that same mathematics and equation to get at the difference in the energy of the two transition states. Now we'll look at a more rigorous example, but that makes it a little simpler. The more rigorous example today is going to come from our textbook on page 370. On page 370 there is a nice illustration and discussion in a connection for you there. So we can take the Arrhenius plot, which is what they did in the connection, and particularly in the literature reference it was taken from, but it's equally valid to use the ratio of the two Arrhenius plots, which we tend to use Arrhenius plots more these days. So you can do the calculation for the formation of the two products, but let's look at this equation first. So we heat the starting material here, this chlorocyclopropane, and, sorry, not heating, in this case they use light, to extrude a carbene. Okay, now here's one of the assumptions. We're assuming that that carbene is in equilibrium and all of its molecular motions are in equilibrium for it to react. And that's going to come up later because in some instances that is not valid, but that's the next video. So then we can measure the rate constant for the formation of two products. One product is the formation of the alkene, illustrated here, and the other product is for cyclopropanation. So we have the product 3 here of rearrangement, or the product 4, the cyclopropanation, where the carbene reacts in a bimolecular fashion, of course, with the alkene present in the reaction. So now, applying our assumption, we can divide the Arrhenius equation for one by the other, that is K over K prime, or in our case, and the way it's done there in our example from our textbook, is the K for the cyclopropanation over the rate constant for the rearrangement and that is plotted versus 1 over temperature. Now this leads to a separate plot that we can see here. The log of the logarithm of the cyclopropanation versus the rearrangement versus 1 over t, and we get a linear correlation. Now this tells us that we're getting a good correlation with our transition state theory, in this case, of the relationship between the two pathways. In these different pathways, we can then backtrack out, and in fact they've done that for us here. We find that the difference in energy is 1.6 kcals per mole. Now this value of 1.6 kcals per mole is of course the delta G transition state for these two reactions. Now for us, in terms of applying these physical chemistry principles to synthetic chemistry, what we will typically do is make that assumption that I said before and illustrated on the previous page. We're going to assume that the two transition states are in equilibrium. And if we do that, we have a simple and direct approach where delta G equals minus RT ln K transition states. And so what we do is we take and assume that the ratio of the products in a kinetically controlled reaction, again, kinetically controlled reaction, are in equilibrium, and that gives us K transition state, or the equilibrium at the transition state based from the ratio of those two products. Now this is not rigorously correct, but it is effective and useful. Okay, now let's take a look at this graphically. What does this mean for us? It means that from the intermediate carbene that was extruded in our system, there are two reaction pathways. One to cyclopropanation, and then the other pathway, and it doesn't really matter where they end up thermodynamically, so I'm just going to stop that there. Doesn't matter where it goes, but what we're looking at here and what we've extracted from this experiment is this delta G transition state. So here are the two transition states, one versus the other. Of course, for this reaction from here to here is delta G transition state, and of course this is delta G transition state for the rearrangement versus the cyclopropanation. But what we can get at experimentally, which is very useful to us, is delta G transition state.